All right, guys, here we go. Pre-calculus, section 9, chapter 9, section 4, homework page 642. Now, this section has to do with math induction. It's one of the more challenging lessons of what we have in here pre-calculus. Okay, math induction is basically trying to prove statements involving a positive integer n. Okay, basically what we're doing is working with proofs, kind of like geometry proofs, but not for geometric shapes and such. But here we're doing proofs using code induction. Okay, so there's three steps involved. Step one, first you're going to prove the conjecture is true for n equals 1. Okay, so basically whatever the statement is, we're going to prove that it works for the first case number n equals 1. And then after doing that, then we are going to assume that it is true for n equals k. And then the last step, we're going to prove that because it works for n equals k, we're going to show that the steps will work for the next number, n equals k plus 1. Okay, so these are my three steps here. So let's do some examples of that. So first example here is prove the sum of the first n evens is equal to n parentheses n plus 1. So what they're trying to have you prove is this. Prove, okay, 2, 4, 6, 8, 10, like that. Okay, prove that when I add all of these up, I can add up as much as I want. Okay, now what we notice that this pattern is 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. And so the generic equation is 2n, okay, where n is the location. Well, I want to prove that this will equal, if I add all these up, it's simply going to be n plus 1. Okay, so what this basically means is, for example, I want to add up any amount of numbers. Okay, let's say, for example, I want to add up when n equals 5. Okay, what this says is that I take the first 5 numbers, okay, not just put 5 in here, but n equals 5. For n equals 5, on the left-hand side, I'm going to take the first 5 numbers, 2, 4, 6, 8, and 10. Now, when I add these up right here, I'm going to get 30, okay? So 6, 12, 20, 10, this right here, when I add it up, is 30, okay? So I can manually add it and I get 30. Or a faster route would just be, hey, put 5, n equals 5 into the right-hand side. 5 plus 1, so 5 times 6 is 30. So on the left-hand side, you can add it up manually. On the right-hand side, instead of doing manually, you're just gonna use the formula, right? So this works for, it doesn't matter how many numbers you put in, okay? So if I pick a random number like n equals, let's say 8, okay? So that means my first 8 numbers. I want to add up the first 8 numbers, okay? 2, 4, 6, 8, 10, 12, 14, and 16, okay? When I add up these 8 numbers, okay? When I add up these 8 numbers here, I'm going to get 30. I'm also going to get 72, okay? When I add up all these numbers, I'm going to get a grand total of 72. See, I did it manually. I got 72. Or, according to this proof here, it says, hey, let n equals 8 and put it into the equation of n plus 1, and you'll get the same exact answer. Let's check. Okay, I'm going to put 8 in here. So 8 plus 1, 72. You see that? So this proof is very powerful. Now, I just showed you that it works for n equals 5, n equals 8. We can keep on doing this forever, right? But that would take a long time. So this proof, it says, how do we know that this works for every single time? Okay, so this is where the induction comes in. All right, so step one, show, we have to write this out. Show true for n equals 1. Okay, that's my first step. I always want to show that it's true, that this statement is true for n equals 1. Okay, so according to this proof, 1 is my first number when n equals 1. That means my first number over here is 2. Okay, I want to show that this 2 equals the amount that I get when I plug in 1 to the right hand side. If I plug in 1 to the right hand side, I get 1 plus 1. Oh yeah, so that works. So my first step, I always want to show that this statement is true for n equals 1. Okay, so now that I've seen that I've shown you n equals 5 works, n equals 8 works, I can show you as many as I want. So that's where step 2 comes in. Step 2 basically breaks down to be, well, now that I've shown you a couple of times, then you kind of believe me then, okay? Then it says now you're going to assume true for n equals k. All right, some random number down the road, k. So in other words, this statement is going to be true for some generic number, some generic location k. In other words, 2, 4, 6, 8, 10, plus, like that. Some random number, n equals k. So I'm going to put k in here. 2k equals k plus 1. So step 2 is very simple. You're taking the original thing you're trying to prove, and you just put in n equals k. Now, step 3 is where all the work is, okay? Step 3, okay? You're going to show true for n equals k plus 1. Okay, so I'm going to show that this example will be true for the next guy. Now that I know that it works for k, I'm going to show that it works for the next guy, k plus 1. So 2, 4, 6, 8, 10 plus ... plus 2k, all right? That's when n equals k. But what happens when n is k plus 1? Well, in other words, the next number, 2k plus 1. All right? So on the right-hand side, I'm going to substitute k plus 1 where I see an n. So this is going to be k plus 1, parentheses, right there, up here. And I'm going to take out n, I'm going to put in k plus 1. I'm going to take out n, I'm going to put in k plus 1. But it's also plus 1 at the end right there. So I'm going to simplify this to be k plus 1, parentheses, k plus 2. Now, I'm going to try to show that the left-hand side is going to be this guy, okay? I have to prove that the left-hand side is going to come out to be this. So here's where my assumption is going to help me. I always use the assumption to help me with my proof, okay? I always use step 2 to prove step 3. If you notice here, 2, 4, 6, 8, 10, ... 2k is part of the proof, is part of the assumption. This, we said, equals k plus 1. The only new thing is 2k plus 1. All right, so now we want to prove that this equals the right-hand side. So there's a couple ways you can do this. You can factor these out. That'll be the fastest way. Or if you can't see that, then what you can do is distribute, okay? A lot of times people have trouble factoring out the k plus 1. So what we can do is distribute here, k squared plus k, and then distribute here, 2k plus 2, and then simplify. This is k squared plus 3k plus 2. Okay, now when you factor this is factorable. This gives you k plus 1, k plus 2. And that is equal to the right-hand side right there. K plus 1, k plus 2. So what we just got done proving is that this statement works no matter what numbers you plug in. So we proved it to be true. All right. So I'll give you some more examples on other videos. Okay. Try to understand that.